The Suffix Array Constructor is a text indexing system designed to generate lexicographically sorted suffix orderings for string data. The primary function constructs suffix arrays through a standard comparison-based algorithm that iterates through input sequences and maintains rank orderings. Input text is assumed to be encoded in UTF-8 format. The system operates on single-threaded execution by default. Maximum supported string length is 2 GB. Construction time complexity is O of n log n, where n represents the input length. The constructor accepts string data through the initialize method, which takes a single parameter of type byte sequence. The byte sequence container holds immutable reference to the source text throughout the construction process. No copying of input data occurs during initialization. The constructor performs validation on the byte sequence to ensure all byte sequences are valid UTF-8. Invalid sequences generate an error code and halt processing. Initialization is non-destructive and may be called multiple times on the same constructor instance. The build method initiates the suffix array construction process. This method takes no parameters and returns an opaque suffix array handle object. Internal processing allocates auxiliary memory structures equal to approximately 8 times the input string length. Memory allocation occurs on the system heap with default alignment set to 64-byte boundaries. The build method is blocking and may require significant processing time for large inputs. Progress callbacks may be registered prior to build invocation but are not required. The internal sorting mechanism uses a modified SAS algorithm based on induced sorting. The algorithm partitions suffixes into S-type and L-type categories according to lexicographic ordering rules. S-type suffixes are those lexicographically smaller than their following suffix. L-type suffixes are greater than or equal to the following suffix. This classification enables efficient recursive reduction of the problem space. The algorithm maintains invariants that ensure correctness of the final ordering. The suffix array handle provides access to constructed orderings through the query method. Query takes a suffix index parameter of type UID64 and returns the text position of the suffix at that rank. The returned position value represents the byte offset from the start of the input string. Query method has constant time complexity. Suffix indices range from 0 to n-1, where n is the input string length. Out-of-bounds queries generate an exception. The rank method performs the inverse operation of query. It accepts a text position parameter and returns the rank of that suffix in the constructed array. This method performs binary search on the underlying suffix array to locate the corresponding rank value. Time complexity is logarithmic relative to input string length. The method returns a rank value between 0 and n-1. Positions beyond the string length return an error status code. Longest common prefix computation is facilitated through the LCP array construction feature. This optional feature builds an auxiliary array storing the length of the longest common prefix between consecutive suffixes in the sorted order. LCP construction occurs automatically when the build LCP array method is invoked after suffix array generation. The LCP array consumes additional memory proportional to input length. LCP array queries have constant time complexity. LCP values range from 0 to the string length. The suffix array constructor supports multi-alphabet text inputs. Supported alphabets include standard ASCII, extended ASCII, UTF-8 multi-byte sequences, and custom application-defined byte ranges. The constructor automatically detects the effective alphabet size from the input data. Alphabet size is recorded in the suffix array handle metadata. Custom alphabet mappings are supported through the setAlphabetMap method called prior to build invocation. Alphabet detection improves algorithm efficiency for sparse character distributions. Range query functionality allows efficient substring searches within the suffix array. The range query method takes a pattern byte sequence and returns a range object containing minimum and maximum ranks of all suffixes, beginning with the pattern. This method performs binary search on the suffix array to locate range boundaries. Time complexity is logarithmic in string length plus logarithmic in pattern length. Empty ranges indicate pattern absence in the input text. Pattern length is limited to the input string length. Memory management for the suffix array constructor follows a standard allocation and deallocation pattern. The constructor allocates working memory during initialization and maintains it throughout the build process. The suffix array handle retains the constructed suffix array indefinitely until explicitly destroyed. Destruction is performed by calling the destroy method or through automatic cleanup when the handle object is deallocated. Explicit destruction is recommended for long-running applications processing multiple strings sequentially. Error handling in the constructor is performed through status codes and exception generation. The initialize method returns a status code indicating success or the nature of validation failures. Build failures generate exception objects containing detailed error information. Exception objects include error codes, descriptive messages, and the input offset where the error occurred. The error handling mechanism is consistent across all public methods. Applications should implement catch blocks for exception type suffix array exception and its subclasses. The constructor provides serialization functionality to persist constructed suffix arrays to disk storage. The serialize method writes the suffix array, metadata, and optional LCP array to a byte stream object. Serialized data includes a header containing format version and checksum information. Deserialization reconstructs the suffix array from serialized data through the deserialize static method. Serialization format is platform independent and uses little-endian byte ordering for all numeric values. Performance characteristics vary depending on input characteristics. Highly repetitive input strings show better performance due to reduced alphabet size. Random input strings exhibit performance near the theoretical O of n log n bound. Small inputs below 1 megabyte typically complete in milliseconds. Large inputs exceeding 1 gigabyte may require several minutes of processing time. Performance scales linearly with thread count when multi-threaded construction is enabled. Benchmark data is available in the Performance Appendix. Advanced configuration options are available through the Configuration Builder class. Options include thread pool size for parallel construction, memory allocation strategies, and progress reporting intervals. The setThreadCount method accepts values from 1 to the system processor count. The setMemoryLimit method enforces maximum auxiliary memory allocation boundaries. The setProgress callback method registers a use-supplied function invoked at regular construction intervals. Configuration objects are applied before calling the build method. The constructor integrates with standard library containers and algorithms. SDL-compatible iterators are available through the getIterator method on the suffix array handle. These iterators enable use with standard algorithms including sort, find, and fold operations. Iterator dereferencing returns suffix position values. Iterator range operations support begin and end semantics consistent with SDL conventions. Reverse iteration is supported through RBegin and rend methods. This concludes the technical documentation for the Suffix Array Constructor system. All primary functionality has been described, including construction, querying, range searching, and serialization features. Advanced options and integration points have been documented. Implementation details regarding the SA's algorithm and memory management have been provided. Applications requiring string indexing and pattern matching should refer to the example code section for typical usage patterns. Additional technical details are available in the appendix sections.